Okay, so let's talk about the naive rule. And to give you a clue or a hint, the naive rule is just the Weka 1R rule. But we're going to talk about it in slightly different terms here, but that's all it is. So the naive rule, which is different than naive Bayes algorithm, is the benchmark to measure all other classifiers. And remember, we talked about it as we talked about 1R as being a benchmark. Okay, it's a very simple, super simple rule for classifying a record into one of M classes. So the class variable can have M different possibilities. And it ignores, just like we said with 1R, it ignores all the predictor information. So we're going to denote the predictor information by x1, x2, x3, and so on up to xn. So like in the iris data set, we had sepal length, sepal width, petal length, and petal width. And then we were trying to predict the class, which was iris setosa and virginica and so on. That was the class, but these were the predictor variables. So we would label these as x1, x2, x3, and x4. In this case, we had 4. And we classify the record means the row, to the majority class. So that means that suppose that we have a record that has a sepal length of 3 and a sepal width of 2 and a petal length of 4 and a petal width of 3. And so what we do is we look at all, maybe we have 150 elements in our training set. So we look for all of the elements that have this sepal length, this sepal width, this petal length, and this petal width. And suppose we have 7 of them with these measurements. Then what we do is we say, okay, well, let's say out of those 7, 3 of them were iris setosa, 2 of them were iris virginica, and 2 of them were the other class. Then which is the majority class? This one, the setosa. So then we will say if we get a new flower or element or row with these measurements, then we will classify it as a setosa. So we classify the record to the majority class. Hopefully other classifiers will do better than this, since they will include information given by the predictors. So the naive rule, or 0R, is a very simple or super simple rule for classifying a record into one of M classes, ignoring all the predictor information. So we're going to ignore x1, ignore x2, x3, xn. Remember that for the iris data set, we had sepal length, sepal width, petal length, petal width, and then the class. And so this would be labeled perhaps x1, x2, x3, x4. In this case, we would have just 4 for the iris, but we could have more in some other case. But we will label them as x1, x2, x3, xn. But we're going to ignore all of this information, and all we're going to do is figure out which class, in the case of the iris, we had the iris setosa, iris virginica, and one more. So we'll just figure out which one in our data set has the greatest frequency. So for example, suppose it was the iris setosa. Then for every new record, we would classify every new record as iris setosa. So that is what we call the naive rule. Okay, next we're going to introduce something called complete Bayes before we go to naive Bayes. So the difference between naive Bayes and the complete Bayes is that naive Bayes makes a simplifying assumption, and that makes the calculations easier. But first we're going to consider the complete Bayes. Complete Bayes is very intuitive. Recall that the whole subject of classification is, in data science, can be summarized by saying that we're trying to decide what class a particular instance should be assigned to. For example, Suppose we're a company that sells chocolate. So a new customer, X, shows up at our doorstep or at our website. Which of our products should we try to sell to him or her? So suppose our products are dark chocolate, milk chocolate, and white chocolate. So here the instance is X, and the classes are the list of our different products. So we are classifying our instance X as being the kind of person that likes dark chocolate, or that likes milk chocolate, or white, or maybe we'll even include the category of none. We say that the four classes are dark, milk, white, and none.